This is the third video in the Propositional Logic module for Foundations of Computer Science. The topic is semantics, with a small bonus discussion at the end of some common equivalences that are helpful when working with formulas. Informally, the term semantics refers to everything pertaining to assigning truth value to our statement. So we will begin with interpretations and truth. The way we define an interpretation is as a total function, and like all functions, it maps one set to another. So we begin with some formula A, and we define the set fancy P sub A to be the set of all atoms appearing in A. These are just all of our propositional variables, P, Q, R, S, etc. And then we define an interpretation, which we represent as fancy I sub A, as a total function from P sub A to this set that contains just two elements, T and F, representing true and false. So in other words, we go through all of the atoms in our set P sub A and we assign to each the value of either true or false. And this is what we call defining an interpretation for a formula. So now that we have an interpretation, we can say whether or not the formula is true under that interpretation. So to define this notion of truth, I say, let I sub A be some interpretation for some formula A. Then we can calculate the truth value of this particular interpretation, I sub A, for that particular formula. And this is called the truth value of A under the interpretation I sub A. We write it as V sub I sub A. There are lots of dependencies, and to keep track of them, we use lots of subscripts, but later we can drop some of these if they are very obvious. This doesn't tell you yet how to actually evaluate the function V. The actual definition of our V is given inductively using the table on the next page. So it's not quite as compact as you might like it to be, but I think if you've used Boolean operations before or seen operations of propositional logic, it'll be fairly intuitive for you to pick it up. This table shows how you would interpret V for some formula A depending on the value of its subformulas. So I know there's a lot on this slide, but if we spend just a moment parsing it, I think you'll see it's not conceptually difficult. What's happening is, remember that we know that all formulas in propositional logic can be expressed as extended binary trees in which every internal node has either one or two children. And so this table tells you how to evaluate the truth value of a parent depending on the truth value of its children. We'll work through an extended example in a moment, but first just look at the definition for the not operator. This is just saying that if a principal operator of some formula is not, then it has one child, which we're calling the subformula A sub 1. And so the value of the formula in this case will be whatever we've determined the value of A sub 1 to be, but then negated. So if the value of A sub 1 is true, it will be false. If the value of A sub 1 is false, it will be true. And this is what our table tells us up here. The value of A depends on the value of A sub 1, what it is the opposite in each case. Likewise, if the root of A is some binary operator, for example, the OR symbol, then A is false if it happens that both of the children are false, and in all other conditions, A is true. This is just the definition of the OR operator. All this table does is just write down all of these evaluation conditions that you already understand how to apply because you understand how to parse equations in arithmetic using an order of operations, and we parse logical sentences using the same strategy. So as long as you know what the meaning of the operator is, this should be pretty straightforward. Now, because Ben Ari uses lots of operators, again, we have these definitions for our NAND and NOR operators and our exclusive OR operator on this table also. So just to make sure this is totally clear, we'll use this table to work through the evaluation of the truth of a formula under a particular interpretation. I think you'll quickly get the hang of how it works. We'll use this formula A, which is P implies Q, if and only if not Q implies not P. This is the same example formula we've used in the previous video, and notice it is not quite the contrapositive. We assign an interpretation I sub A in which we say we're going to map the value P to false and the value Q to true. And now that we have an interpretation, we can determine whether or not the entire formula is false or true under that interpretation. And we'll use the table on the previous slide, but actually you probably don't even have to look at that table. Just to be very precise, I'll draw this out as a tree. You probably already know there are several ways you could evaluate this and get the right answer as long as you go from bottom to top. We'll go from the left to right, starting with P, until we've completed the left child, and then we'll start again from the bottom of the right child, as you would expect. In the formula, that means we'll do the left side, and then the right side, and then the whole thing. This order gives you what we're calling the inductive evaluation of our function v. According to our interpretation, we have assigned the value of p to false and the value of q to true. So now we have false and true, and these become subformulas of the parent node. Since we know the implication is true whenever the antecedent is false, we now know that the parent is true. If you want to tie this back to the formula without drawing a tree, that's of course fine too. Write false, true here, and this whole expression is true. Moving on, of course, we are unable to evaluate whether the whole statement is true or false until we evaluate its right child also. So again, we start at the bottom. And since we've assigned the value of true to q and false to p, it's clearly the case that not q is false and not p is true. So now we move up again to evaluate the implication, and again we have false implies true. So the antecedent is false, and therefore the whole implication is true. Now to summarize, our left child is true, and our right child is true. So our bijection is saying true if and only if true. And under this particular interpretation, that is true, and therefore the whole formula evaluates to true. Now that we know how to define an interpretation for a single formula, it's fairly easy to extend this to a set of formulas. Informally, all we do is assign a truth value to every atom in all the formulas in the set. The only thing we have to be careful about here is that if we assign some atom a particular value in one formula, it has to be the same value in all of the formulas in which it appears. We start by defining our set of formulas S, and this time our set of atoms is just the union of all our previously defined sets of atoms for each of the formulas in our set of formulas. So this sort of complicated looking statement here is just saying this is the set of atoms that appears in all of our statements. The set of atoms in each particular statement is just this P sub A, just like before, and we have this little I to index exactly which of our statements it is. Using a set here to represent all of our atoms just means that because the elements don't ever appear twice in a set, we can't possibly assign different values to the same variable. In any case, from here on out, our definition of an interpretation is exactly the same. The interpretation over the set, I sub s, is a total function that assigns every propositional variable in that set a value of either true or false. We can then evaluate the truth value of any formula in our set, just as before, using our inductively defined v for this particular interpretation on this particular formula. And again, this gives us a truth value of our formula A sub I under the interpretation fancy I sub s. There's nothing new about the way we evaluate the statements. It's again just as it was in our previous example. This final bullet is just emphasizing the warning that the only thing we can do wrong here is that you could make the mistake of saying that a proposition is true in one formula and false in another. That can't be the case if we're talking about an interpretation for a whole set of formulas. The way the definition guarantees this is by using this union of all the sets of atoms. Now that we have a way of defining truth values of formulas, we can also say whether two formulas are equivalent to each other. And this is a very useful thing to be able to do when we're simplifying expressions or transforming them for some purpose. The definition of logical equivalence of two formulas is very simple. If we have two formulas, A sub 1 and A sub 2, then we say these two formulas are equivalent if and only if they have the same truth value under all interpretations. To express this concept of equivalence of formulas, we use these three horizontal bars, and this is read as A sub 1 is equivalent to A sub 2. As kind of a side note, it's important to keep track of the difference between your symbols for bijection and logical equivalence. These have different meanings. The bijection symbol is a Boolean operator in propositional logic. It appears inside the formulas in the logic. For example, we might say P and Q if and only if R implies S, something like this. Here the bijection symbol is appearing within a single formula. The equivalence symbol, on the other hand, is not a Boolean operator. It does not appear in the expressions of propositional logic. It describes a property of pairs of formulas, not pairs of propositions, but pairs of whole formulas. So one way to express this distinction is to say that the equivalence symbol is part of the meta language that we use to reason about propositions. One way to express this distinction is to say that the equivalence symbol is part of the meta language that we use to reason about the formulas of propositional logic, rather than being part of the language of propositional logic itself. Now, having said that, it's very reasonable to think there must be some connection between the meaning of these two symbols, and even though we want to keep them separate, there is in fact a connection. And it is expressed by this theorem, which is that A sub 1 is equivalent to A sub 2 if and only if combining these two formulas to form a new formula with the bijection operator creates a statement that is true for every interpretation. Unfortunately, this notation is a little bit confusing because I just said that the bijection operator appears inside formulas of propositional logic, and here it is seeming to appear between two formulas, A sub 1 and A sub 2. So just to explain this, what's happening here on the right side of this sentence is we're assuming we're going to substitute whatever A sub 1 and A sub 2 say. We're treating them as children or subformulas of the new formula that we're building, which is the whole thing. Another direct consequence of having a way to evaluate the truth values of formulas is that we notice that there are some special formulas that are always true or always false. It is convenient to define constants that indicate this. Ben Ari uses the italicized words true and false for this purpose. Sometimes for the constant true, you'll also see this top symbol, which looks like a skinny capital T, and the way this constant formula works is that it always evaluates to true under any interpretation. You can treat it as equivalent to any statement in propositional logic that is always true, such as, for example, P or not P. Some texts will just use this expression instead, so you can just think of this as like a shorthand for that statement if you want to. On the other hand, it's just a little bit more readable to write true. Likewise, the constant formula false is sometimes written as a bottom symbol or an upside down skinny T, as I call it. It always evaluates to false under every interpretation, and it's exactly equivalent to any contradictory statement, like, for example, P and not P. Generally, adding these constant formulas makes things more clear, but there is one small hazard, which is you have to make sure you don't get them confused with the T and F values that we are assigning to our propositional variables. When we write out the words true and false, we're talking about whole formulas, and furthermore, these are constant under all interpretations. They are distinct from the actual values that we use to assign interpretations. To say this yet another way, there's two levels of truth here. There's truth at the level of individual atoms and truth at the level of formulas. But truth at the level of formulas or falsity at the level of formulas means something a little bit different. It means it doesn't matter what interpretation you give to those atoms. These formulas will be true or false anyway. That mostly wraps up what I have to say about semantics. So we're now entering the bonus round of the video in which I just give a quick run through of some logically equivalent formulas that can be useful for rewriting statements. Most of these I will skim over very quickly because they are very easy to verify and exactly analogous to what you would get evaluating propositional variables. We're just extending those properties to formulas. You should make sure that you understand all of them. The ones that are important will come up again when we get back to normal forms. So first, using the true and false constants we just defined, we can immediately create a bunch of logically equivalent formulas that help us simplify things. For example, if we combine two subformulas with an OR, and one of these subformulas is the constant formula true, then the whole expression evaluates the constant formula true. This should not be surprising. It is in keeping with the normal behavior of the OR operator. Generally, you can just check these by looking at the truth table and the definitions of the operators. There are a few handy ones you might not think of off the top of your head, such as simplifying A implies false to not A, or A XOR true to not A. The second half of this slide is similar in spirit to the first half, but it just shows you where you can eliminate or simplify redundant operators. The next convenient application of equivalence is to express the commutative, associative, and distributive properties for our various logical operators. Starting with commutativity, not all logical operators are commutative. An obvious exception is that the implication cannot be reversed, but quite a few of these operations are commutative, and we can just express this by writing the equivalence of these two formulas. Another convenient property to know about is associativity. Again, this is something you could easily work out for yourself, but what the table here shows is just that OR and the bijection operator and the XOR operator are all associative. Distributivity is a little more interesting. This is an operation that will definitely come up later when we talk about normal forms. The rule that's being expressed says that it's allowable to distribute a disjunction over a conjunction and a conjunction over a disjunction. In the first case, you get A or B and C is equivalent to A or B and A or C. And in the second case, you get A and B or C is equivalent to A and B or A and C. Now, finally, this last set of equivalences gives you some useful ways of eliminating operators by replacing them with more primitive operators. So if you started with all of the operators Ben Ari uses, but you want to get down to only a few operators like and, or, and not, which is something that we definitely will want to do, this would be a useful reference slide for that. I think it's worth talking through these briefly, even though you can verify them on your own, just to make sure that the intuitive meaning is clear, because I think that prevents you from having to memorize them. So the first expression, A if and only if B, can be written as the conjunction of implications in both directions. A implies B and B implies A. We've actually used this equivalence already in our proofs, so I think you're probably familiar with it. A closely related statement is XOR. This is just the negation of the bijection. If the bijection is true, it means that A and B are always true or always false at the same time. If XOR is true, on the other hand, it means that A and B are never both true or both false at the same time. So it's not too surprising that the equivalent statement here is just the negation of the statement on the previous line. If we distribute this negation through using a De Morgan's law, we will get the line below to reverse, of course, the center. And what this statement means, if we read it intuitively, is that it is not the case that A implies B, or it is not the case that B implies A. Next, this third equivalence is surprisingly important. A implies B can be written as not A or B. This is another one you'll definitely see again. Most people need to look at the truth table to verify this because it is sort of famously not that intuitive. And if there's any one of these that you want to memorize, this is it. A less common way of rewriting this expression is just to write it as the double negation of the previous expression using a De Morgan's law. So what I mean is we can take this expression here, say it is equivalent to the negation of itself, which is always true. Then using a De Morgan's law, we can distribute the negation symbol through, negate both sides of the expression, and flip our OR symbol to an and we get an expression that is identical to the one on the line below. The next two equivalences use exactly the same trick. They just double negate themselves and then use a De Morgan's law to distribute the negative through. And what these tell you is just that if you ever need to translate an OR into an and or an and into an OR, you can do this in this way. Finally, these last two are a little bit tricky, but it follows from the fact that A implies B is equivalent to not A or B, that A or B is equivalent to not A implies B. You can show this by just applying the rule above to the right side. We treat not A as a single unit, and we apply this equivalence that we've already looked at, and we end up with not A or B, which is the same as A or B. So that verifies that this equivalence is correct. Likewise, if we start with this equivalence A and B here, and then apply to this inner expression not A or not B a very similar transformation to what we just applied, we will end up with A and B is equivalent to not A implies not B. I'll let you walk through and verify that for yourself, but I've kind of sketched how you would do it. In general, I would treat these equivalence slides as a reference table, but if you're having trouble seeing why any of them are true, you should sit down and try to figure them out. There are a few that, as we mentioned, are kind of important. I would say certainly this first one, and also the third one, which I pointed out before, and then perhaps also the second from the bottom. These could all be helpful to have at your fingertips going forward. So that completes our video on the semantics of propositional logic and also our bonus section on equivalent formulas.